Welcome to this deep dive into pigment volume concentration or PVC and its critical counterpart, CPVC, tailored for you as an R&D professional formulating automotive polyurethane and polyaspartic coatings. Imagine your dry paint film as a carefully packed brick wall. Pigments are the bricks providing color, opacity, and structure, while the binder acts as the mortar holding everything together. PVC quantifies just how much of that wall is bricks versus mortar, specifically the percentage of pigment volume in the total volume of dry solids, excluding solvents that evaporate away. This single number serves as the cornerstone for every formulation decision in your lab, dictating gloss, durability, breathability, and cost. The formula for PVC is straightforward yet powerful. PVC equals the volume of pigment divided by the sum of pigment volume and binder volume, multiplied by 100%. To get those volumes, take the weight of each component and divide by its specific density or gravity. Think of it as converting kilograms of wheat into liters for a recipe. Pigments like titanium dioxide might have a density around 4.2 grams per cubic centimeter, while polyurethane binders hover near 1.0 to 1.1. Solvents don't count here. We focus only on the final dry film. For instance, in a simple white automotive primer batch used by Indian manufacturers for truck underbodies, say you have 25 grams of TiO2 pigment, 20 grams of talc extender as a filler, and 50 grams of solid binder resin. First, calculate TiO2 volume. 25 divided by 4.2 equals about 6 cubic centimeters. Talc at density 2.7 gives 20 divided by 2.7, roughly 7.4 cubic centimeters. Total pigment volume is then 13.4 cubic centimeters. Binder volume is 50 divided by 1.0, or 50 cubic centimeters. Plug into the formula. 13.4 over 63.4 times 100% yields about 21% PVC. In real polyaspartic jobs for fast-cure bed liners on Indian commercial vehicles, adjust for binder solids content. If it's 70% solids and solvent, scale the binder volume down accordingly to avoid overestimating. We focus examples on polyurethane and polyaspartic coatings because these dominate your automotive specialty work in India. Polyurethanes for flexible OEM topcoats on passenger cars, and polyaspartics for rapid cure protective layers on heavy-duty trucks and construction equipment. They demand precise pigment loading to handle India's humid, dusty conditions and substrate flexing, unlike slower curing alkyds in architectural paints. Now enter Critical Pigment Volume Concentration, or CPVC, the magic threshold where your formulation teeters between robust performance and failure. CPVC is the highest PVC at which the binder perfectly wets and fills all the voids between closely packed pigment particles, leaving no excess air pockets. Push beyond it and the film turns porous like Swiss cheese. Stay under, and you have surplus binder sealing everything tight. To estimate CPVC, use pigment oil absorption, grams of oil needed to wet 100 grams of pigment, combined with densities. The formula breaks down like this. First, multiply pigment density by oil absorption to get a factor representing how much binder the pigment demands. Divide that by 93.5, which approximates the density of linseed oil times 100 for unit consistency. Add 1 to account for the binder's own volume share. Then take 100 divided by that sum for the percentage. For TiO2 with density 4.2 and oil absorption of 20, calculate inside. 4.2 times 20 equals 84, divided by 93.5 equals about 0.9, plus 1 equals 1.9. Then 100 over 1.9 yields roughly 53% CPVC. Extenders like talc, with higher oil absorption around 50, drag CPVC down to 30 to 40%, while spherical pigments pack tighter than flaky ones, shifting the number up or down. These concepts hit film properties hard, especially in demanding automotive applications where polyurethanes flex with metal panels and polyaspartics cure lightning fast on shop floors under low humidity conditions. Below CPVC, excess binder forms a continuous film. Think glossy topcoats shining on showroom passenger cars, with top-tier durability against scratches, chemicals, and UV fade from Indian monsoons. Porosity stays ultra-low, blocking water and corrosion like a fortress. Flexibility shines for crack-free bends. At or above CPVC, the surface roughens for a matte finish, boosting hiding power so fewer coats cover prime truck steel. But durability plummets. Brittleness invites cracks. Porosity lets moisture in, accelerating rust or chalking. Density drops as air voids multiply, and stain resistance tanks. In your world, Automotive clears target 10 to 30% PVC for that wet look gloss. Primers climb to 50% or more for adhesion and opacity. Always hugging just below CPVC to balance cost without sacrificing integrity. For polyaspartic systems, which excel in fast cure bed liners and truck coatings for Indian logistics fleets, formulating around CPVC demands precision tweaks. Their rapid cross-linking tolerates higher PVC, up to 55 or 60% better than slower urethanes. But exceed it and haze creeps into clears or adhesion fails on ABS substrates. Start by blending pigments. Pair low oil absorption TiO2 with high absorption calcium carbonate to fine-tune CPVC downward for matte textures. Add dispersants and wetting agents to ensure binder sneaks into every nook, preventing flocculation. Empirically test by ramping pigment loads in lab mixes, draw down films, and watch for gloss crash via reflectometer or porosity via water uptake on Q panels. Standard pre-weighed steel or aluminum test panels used globally to simulate real substrates for standardized performance checks. Target 10 to 15% below calculated CPVC for a safety margin, especially on flexible auto parts. Polyaspartics forgive more, but still hate voids, weakening tensile strength. Use Excel or coding software to iterate fast, inputting real densities from supplier TDS sheets, and validate with drawdowns under low humidity to mimic shop conditions. Mastering PVC and CPVC isn't theory. It's your edge in scaling formulations from bench to production for Indian OEMs. Low PVC hikes costs with excess resin, but delivers premium finishes. High PVC slashes resin use for budget primers, yet risks rework from poor performance. In automotive polyurethanes, vibration and thermal cycling amplify above CPVC flaws, so always overbind for longevity. Experiment this week. Tweak a polyaspartic batch, measure PVC, bake panels, and test bend. Watch the science unfold. Drop any technical questions you want to discuss in the next episodes in the comments below.